Hey guys, welcome back. So today we're going to be talking about topic 1.6, photoelectron spectroscopy. This is a pretty simple procedure. The application of it actually is pretty simple, but the nuts and bolts of how it actually works may be a bit more complicated. The way I'm going to go through it is we have this kind of worksheet that kind of lets you follow along and kind of see how a photoelectron spectroscopy actually works. So that's exactly what I'm going to do today is just kind of run through this, and then you can print this out or download it. There's a link in the description below to get a copy of this worksheet. First off, I'm going to talk about a soccer player that's in a ditch. If a soccer player is in a ditch and he needs to kick the ball, if he doesn't kick the ball hard enough, of course the ball is going to go up and then go right back down. But if he kicks the ball with just the right amount of energy, he can get all the way up to the very top of the hill, and then the ball just stops. If he kicks it too hard, the ball is going to go all the way up and then start rolling, continue to roll for a little bit. So right now he needs 45 joules of energy to get the ball out of the ditch. So a couple things. Let's kind of run through this. This is the scenario we're currently working with. Let's go through and answer these questions. What force of attraction is keeping the soccer ball at the bottom of the ditch? Well, gravity. Gravity is the thing that's keeping it down. I think everyone kind of knows that. What type of energy must be overcome to get the ball out of the ditch? So the ball has a certain amount of potential energy here. If the ball is up here, it has more potential energy. We're going to have to overcome the potential energy of this potential energy difference of this hill to get the ball up and out of this ditch. What type of energy must the ball have to get out of the ditch? So it's moving out of the ditch, it's rolling up, so it has to have kinetic energy. So how much energy must be given? We've already said, you can see up here, 45 joules. So what happens in this scenario if the ball is kicked with 30 joules of energy? If it's kicked with 30 joules, that's not enough energy to go up here, so it's going to roll up and roll right back down. If it's 45 joules exactly, it's going to roll up, stop, and have zero kinetic energy left over. But if it has kicked with 60 joules of energy, then the ball is going to roll up and continue to keep rolling. It's going to have a certain amount of kinetic energy left over, so the ball keeps on rolling. How much potential energy is going to be left? So for question 3, how much kinetic energy does the ball have when it reaches the top of the hill, top of the ditch? For 45, the kinetic energy will be 0. And for 60, it will be, 15 joules of energy. So it's going to be continually moving at 15 joules. 5, construct an algebraic equation which shows the relationship between the energy of the player's kick, and the potential energy of gravity on the ball, and the potential energy of the ball when it leaves the ditch. So what we can do is going to go through, we have a certain relationship here. We have KE, kick, and we have PE for potential energy, and we have KE roll. So how much kinetic energy does it have whenever it's rolling? What do you have to do to get one thing out of this? How do we want to arrange this in a equation? Well, what did we actually do before? We took the kinetic energy of the ball that was kicked, and we subtracted the potential energy of the gravity on the ball, and that got us the kinetic energy of it rolling. So, Ke kick minus potential energy equals kinetic energy of it rolling. That is going to be kind of what is going on in this scenario. This has nothing to do with chemistry. It is an analogy of photoelectron spectroscopy. So here we have a model of a hydrogen atom. There's a proton in the center that has it's positively charged, an electron orbiting around in the first energy level with a negative charge. This electron is being attracted to this proton so the electron is being attracted to the proton based on its electrical charge. Positive and negative thing will attract together. And the kick is actually going to come in the form of a photon. A photon is a wave that has a certain amount of energy. So that photon is going to smack into the electron and give this electron some more energy. It's going to try to pop it up into a higher energy level. So there's going to be a certain amount of energy which is required to get this from a 1s orbital to a higher energy level, like a 2s orbital. That's kind of how all of these relate. Let's go through and answer these questions. So what force of attraction holds the electron in the hydrogen atom? Again, is that electromagnetic force? What type of energy needs to be overcome? Potential or kinetic? Potential. What is supplying the energy to remove the electron from from the atom in model 2? It's the photon. So if you were to fill this guy out, gravity is the electromagnetic force, the ball is the electron, the player's kick is the photon. What happens if the photon is less than the minimum energy needed to eject the electron from the atom? What happens to the electron? Well, it's going to increase with energy, decrease, de-excite, emit a photon, and stay at the same energy level, stay at the same orbital. Now, if a photon is exactly at the minimum energy needed, it will eject, but it won't have any more kinetic energy. It won't move anywhere. It'll just poof and be done. What if the photon has more than the minimum energy needed to get the electron out of the atom? Well, it's going to eject, but it's going to eject with some force. It's going to have additional kinetic energy left over, just like the ball rolling after it gets out of the ditch. So the amount of energy necessary to overcome the electron is called the ionization energy. The ionization energy is the same as that potential energy of potential energy difference that the ball had, that 45 joules of energy. That is going to be the same as the ionization energy in the atomic model. Okay. What is the relationship between the ionization energy and the net attractive force which holds the electron in the atom? So it's going to be the same value, but it's going to be the opposite sign. So we have a certain net attractive force which is holding the electron in place, and we're going to need to overcome that. If we want to talk about up here in the ditch example, if we're moving down, we are losing potential energy, and if we're moving up, we are gaining potential energy. Then the ionization energy is the amount of energy I need to put into this ball to get it up. And the potential energy, the energy of the atom keeping the electron in the ditch, is going to be this negative 45. Anything going down on these energy diagrams, remember, is negative. Anything going up is going to be positive. So number 11. So the electrons that escape the atom after bombardment are called photoelectrons. Why is this an appropriate name? Because chemists are bad at naming things. Because we try to keep things very, very simple. These are electrons that have been removed using photons. So they're photoelectrons. Chemists are not clever at naming things. Remember electron repulsion? An electron and electron repel each other. It's called electron repulsion. Break equation. This is going to be the exact same equation as before. Here you have the potential energy of the photon minus the ionization energy, and this is going to equal the kinetic energy of the electron. That's why we use the ball kicking analogy. If the kinetic energy of a photon is exactly equal to the ionization energy, the kinetic energy of the photoelectron should be 0. Verify your equation is consistent with this idea. It is. Consider the equation you wrote in 12. What piece of data do you know to calculate the ionization of a given electron? Do you need to know of a given electron? So to figure out the ionization energy, we need to figure out two things. If I don't know the potential energy of a so I'm going to write this equation up here. Kinetic energy of a photon minus the ionization energy equals the kinetic energy of the electron. Okay, so if we're trying to figure out IE, we're trying to figure out the ionization energy, what two pieces of data do we need to know? Well, we need to know the kinetic energy of the photon, and this is going to be fine because in a photospectrometer, we're going to be able to control this. This is going to be the knob that we're going to be able to turn. And then we also need to know the kinetic energy of the electron. How fast are these electrons actually moving? So those are the two pieces of information we need. Then we can go through and calculate our ionization energy. Okay. So a photoelectron experiment is performed with a simple silicon using sample of silicon, silicon using photons of an energy at blah blah blah. Photoelectrons that generate have kinetic energy of blah blah blah. What's the ionization energy? For this, it's going to be pretty simple. We have photons with a certain energy, and then we have the kinetic energy of the electrons. We have our two things. If we wanted to rearrange that equation, it would be the ionization energy equals the kinetic energy of the photon minus the kinetic energy of the electron. So for this, we're just going to need to know the take 1.4 minus 1.3, 1.43 minus 1.34. If we do that, I just need a calculator because I don't want to make mistakes. 0.09. So in that case, our ionization energy is going to be 0.09 times 10 to the fifth. I don't like that though. I'm going to bring this down a little bit more and say 9 times 10 to the 7. There we go. All right, that is going to be our ionization energy. Hooray! Previous question, was only one atom silicon involved or were many atoms involved? This is going to be an example of making sure you look at your units. Here, we're saying it is 1.3 times 10 to the fifth kilojoules per mole. So that means we're dealing with not one atom, but many, many atoms. So just the fact that our units say this is per mole, then that's going to, we're going to assume that we're using more than a single atom in this. Second one, multiple energy levels. So now we're dealing with multiple balls. If we're going through and looking at this ditch, who's going to need to put more energy into it, A or B? Who's going to need to put more energy into their kick? Well, obviously, A is going to need to kick at 45 joules to get the ball up and over, while B has to kick at 30 joules. Okay. Consider the electron or the atom here. Which electron, 1 or 3, will be require more energy to remove? 3 is going to be easier to remove. It's further away, and since it's further away, remember, coulombic forces have to deal with the charges of the two particles, so the nucleus and the electron. Think about the charges, but you also need to think about the distance between them. I'm assuming that the nucleus is going to be the same for 1 and 3, the same charge. Each electron is going to be the same charge, so charges aren't any different. The thing you need to look for is now the radius. So what is the distance between this nucleus and electron 1, the nucleus and electron 3? 1 is closer, so that force is going to be greater, so that ionization energy is going to be greater. Compare electrons 1, 2, and 3 in terms of their ionization energy. So 1 and 2 are going to have the same, since they're at the same orbital, the same 1s orbital. 3 is going to have less of an ionization energy than 1 or 2, because it is further away. A large number of lithium ions were ionized in a PES experiment, each losing one randomly chosen electron. Which ionization energy will be reported more often? The lower ionization energy or the higher ionization energy? Justify your answer. So which one is going to happen more often? If I randomly pick one of these three, let's say the ionization energy for 1 and 2 is going to be, it's greater than 3. So let's say that the ionization energy for 1 and 2 is 10. Okay? And the ionization energy for 3 is 5. I'm just making up these numbers. But if I were to go through and randomly pick one of these, and all I can tell is the ionization energy, which number am I going to pick more of? So if I randomly pick out 1, I see 10. If I randomly pick out another number and I pick 2, I see 10. If I randomly pick out another number and hit 3, I'll see 5. Which one of the numbers is going to be more often? Well, it's going to be 10, because I have 2 things that are going to give me 10 and only 1 thing that's going to give me 5. So the photoelectron spectra for lithium is shown here. First off, let's go through and look at the graph, look at the axes on our graph. So what are the units for the x-axis? This is your ionization energy in kilojoules per mole. Is something weird about this axis? Yes. If you notice that it's flipped, we start with 0 all the way on the right-hand side, whereas our larger numbers are going to be on the left-hand side. There's a reason for this, and you'll see that shortly. Which of the peaks in the graph represents electrons that are more tightly held by the nucleus? Explain your reasoning. If something is more tightly held, that means it has a higher ionization energy. So this first peak are going to be the electrons that are more tightly bound together, more tightly bound to the nucleus. How many atoms of lithium were ionized theoretically in order to obtain the data from the spectrum above? A mole. I'm going to say a mole. Based on the units, we have a mole. So based on the energy values of the peaks, label each peak with the electrons in lithium atom. See Model 3 for which which ones they have. So based on this, we know that this peak is pretty high. In other words, we're getting more photoelectrons coming off in this range. And here we're getting less. In fact, we're getting about half as many electrons coming out over here. And over here, we're having ones that have a much higher ionization energy, therefore much greater inner atomic forces. So looking at the atom here, 1 and 2 are close together. They are close to the nucleus. They're going to have a larger ionization energy than 3. And since there's 2 of them, we're going to see at the same energy level, we're going to see them have more intensity. Again, if I'm going through and just pulling these out randomly, I'm going to get 1 or 2 more than I'm going to get 3. If I wanted to go through and actually label these, this would be 1 and 2, and this one would be 3. Why are there only 2 peaks and not 3? Well, again, because 1 and 2 are going to give off the same ionization energy. Why is the higher energy peak about twice as high as the lower energy peak? Well, again, that's because there's 2 electrons there. What is the number of peaks in the PES spectrum reveal about the energy sublevels occupied by the electrons in the atom? This is what the functional use of photoelectron spectroscopy actually is. So that means that if you look at this spectrum, I know that the electrons that are going to be with the highest ionization energies, those core electrons, the one in the first energy level, the one in the energy level 1s, are going to be happening first. And I already know that energy level 1s is going to have two electrons in it. So this peak represents two electrons coming out of it. The next peak that I'm going to see are the energy the next peak I see is going to be representing the electrons coming off the next highest energy level. In this case, I know it's going to be 2s. And since that this peak is half as high as the 1s2 peak, I know this is going to be 2s1. So this is going to be how you can go through and look at a photoelectron spectra and look at photoelectron spectra and write out its electron configuration. So based on this, let's go through and actually put that knowledge to use. This is a photoelectron spectrum of neon, and in it, we can go through and even just start writing out. This very highest ionization energy is going to be 1s, and we know it's going to be 1s2. So this must be equal to electrons. The next highest energy is going to be your 2s, and it's the same height, so I know it's 2. Then this next peak is going to be my 2p electrons. And this is, if I look, that's about 1, 2, 3, 4, 5, 6, 7, 8. It's about 4 times as high as the 2 electron peak, so it's going to be 8 electrons. So it's 2p8. And they even told us that this is neon. So we already know what neon's electron configuration is based on just our periodic table knowledge and things like that. We can double check to make sure that this is actually the correct spectrum. And indeed it is. So which shell down here best matches the spectrum? Well, we have 2 electrons in the 1s, and we have 8 electrons here in 2 energy level. That isn't really what we see here. We see 3 separate energy levels. So this particular model, it's a Bohr model that includes the suborbitals. So 1 energy level 2 and 2s and 2p. This is going to be the better representation. Looking at model 4, using the lithium PES as a starting point, show how the spectrum of the next larger element, beryllium, might be different. Recall that beryllium has 1 more proton in its nucleus and 1 more electron in its sublevels. So the things that you're going to need to know are that it's going to have an additional peak that's about half as high as this for our 3s1 peak. But additionally, there's one more thing, that there's an additional proton here. So if there's an additional proton here, that means the force of these, the ionization energy of these inner core electrons are going to be greater. Now we have a more of a charge here. Remember Coulomb's law, charge and radius are going to affect the force. So the charge went up by 1 because we added a proton, and that means this distance, this force is going to be greater. So this force for the 1s is somewhere between 90,000 and 80,000. So I'm going to just move it to shift it this way just a little bit. So let me bring it back here. Okay, so I'm going to shift it just about right here. So this is going to be my first 1s2 peak, and then my second peak is going to be about there. My third peak is going to be 8 electrons. So it's 1, 2, 3, 4, 5, 6, 7, 8. And then real close to the end here, I'm just going to have a small 1 electron peak for the 3s1. So this is going to be the photoelectron spectra, the PES for beryllium. Okay, so for the rest of this, I think what I'm going to do is have you guys go through and use this as some homework and some practice. The Here you see phosphorus and sulfur. They give you 2 different ones, and then there's going to be questions about it. I want you to go through. It's just 1, 2, 3, 4, 5, 6 different questions about sulfur and phosphorus. Go through. I would like you guys to go through and do that. If you have more questions about it, let me know, and I'll be able to help you out. Okay. That. See you guys later.